All right, let's get into it. Today, we're digging deeper than just the average. We're going to talk about the real story your data is telling. And to do that, we need to understand measures of dispersion. These are the tools that show you not just the center of your data, but how spread out or, dispersed it really is.
I mean, really think about it. If someone tells you the average daily temperature somewhere is a perfect 75 degrees, sounds great, right? But what if that means some days are a blistering 110 and others are a freezing 40? The average completely hides that reality. It's a good starting point for sure, but it often buries the most interesting details.
Okay, check this out. This example makes it super clear. We've got two classes, and both, get this, both have an average test score of 81%. If you only saw that number, you'd think they're identical. But look at set A on the left. The scores are all bunched up right around that 81. Super consistent performance. Now look at set B on the right. Whoa! Scores are all over the map, from a 53 all the way up to a 99. Same average, but a totally different picture. This right here is exactly why we need to measure dispersion.
So, to really understand these different stories, we're going to build out our very own statistical toolkit. We'll kick things off with the simplest tool, the range. Then, we'll level up to something more robust, the Interquartile range, or IQR. After that, we're breaking out the heavy machinery, variance, and its way more user-friendly cousin, standard deviation. And then we'll wrap it all up.
First up in our toolkit is the range. It's the absolute quickest, most straightforward way to get a feel for how spread out your data is. It's a first look, but as we'll see, it's a little flawed.
And the formula is, well, it's exactly what it sounds like. You just take the highest value and subtract the lowest value. Easy. So for that consistent class, set A, the range might be pretty small, maybe 86 minus 74, which gives you 12. But for set B, it's 99 minus 53. That's a massive range of 46. It's fast, it's simple.
But, that simplicity? That's also its biggest problem. Imagine in that consistent class, just one student totally bombed the test and got a 35. Suddenly, that one single score blows up the range, giving you this completely distorted picture of how the class actually performed. The range only cares about the two most extreme points and completely ignores everything happening in between. It tells you the possible spread, not the typical one.
So how do we fix that? How do we deal with those pesky outliers? Well, we bring in our next tool, the Interquartile range, or IQR. And this one is much, much more robust. The IQR has a really clever way of dealing with outliers. It just ignores them. It does this by focusing only on the middle 50% of your data. So you line up all your numbers from smallest to largest, you find the point that's 75% of the way through, that's Q3, then you find the point that's 25% of the way through, that's Q1. And the IQR is just the difference between them. By lopping off the bottom quarter and the top quarter of the data, those extreme values just don't affect it.
In fact, the IQR is so useful that it's the foundation for one of the most common ways to spot outliers. It's called the 1.5 times IQR rule. You figure out your IQR, multiply it by 1.5, and then you create these fences. You subtract that value from Q1 for your lower fence, and you add it to Q3 for your upper fence. Anything that falls outside those fences, bam, potential outlier.
Okay, but wait a second. Why 1.5? I mean, this is something that gets a lot of people. It kind of feels like a number someone just pulled out of thin air, right? Why not 1? Why not 2? Well, believe it or not, there's some really elegant math hiding behind that number.
And this table just lays it all out beautifully. If we assume our data is roughly bell-shaped or normally distributed, we can see what happens with different multipliers. If we used a multiplier of 1, our fences would be way too close to the middle. We'd end up flagging about 4.3% of perfectly good data as outliers. That's just too strict. But if we use 2, the fences get pushed so far out that it becomes too lenient. We probably missed some really important outliers.
So that 1.5, it hits the sweet spot. A multiplier of 1.5 puts those outlier fences at roughly plus or minus 2.7 standard deviations, or sigma, from the mean. And that is a fantastic approximation of the famous 3 sigma rule, which says that 99.7% of all data in a normal distribution should fall within 3 standard deviations. It's the perfect balance. It's not arbitrary at all. It's a really smart rule of thumb. All right, time to move on to our third tool, and this one's a powerhouse, variance. See, unlike the range or the IQR, which only look at a few specific points, variance takes every single data point into account. It gives us a much more complete picture of the spread.
So how does it work?
Well, it calculates the average of these squared differences from the mean for every single point. But why square them? Good question. First off, if you just added the regular differences, the positives and negatives would all cancel out and you just get 0, which is useless. Second, squaring makes sure the result is always positive, because you can't have a negative distance. And finally, and this is key, squaring gives a lot more weight to points that are far from the mean. This makes variance super sensitive to those big deviations.
Now you'll see two different formulas for variance. If you're lucky enough to have data for an entire population, the whole shebang, you divide by n, the total number of points. But let's be real, most of the time we're just working with a smaller sample, and in that case you have to divide by n-1. This little tweak is called Bessel's correction, and it is super important. It corrects for the fact that a small sample usually underestimates the true spread of the bigger population it came from. It gives us a much better unbiased guess.
Okay, so variance is this amazing mathematical engine, but it's got one giant practical problem. Its units are all squared. So if you're measuring height in feet, your variance is in square feet? What on earth is a square foot of height? It makes no sense. And this brings us to our final and probably most famous tool, standard deviation.
This quote just nails it, doesn't it? If your data is in dollars, the variance is in squared dollars. It's mathematically correct, but it's impossible to explain to anyone in a meaningful way. It's totally unintuitive. And the solution is so simple, it's beautiful. The standard deviation is just the square root of the variance. That's it. By taking the square root, we undo that squaring we did earlier, and we bring the measurement back into the original units of our data. Dollars, feet, percentages, whatever. Now we're talking.
So here's the final showdown. Think of variance as the powerful engine under the hood. It's absolutely crucial for other more advanced statistics. But standard deviation, that's the dashboard. That's what you use for practical, everyday communication. It gives you a single, intuitive number that tells you the typical, or standard, distance any given data point is from the average. And just like that, our statistical toolkit is fully stocked. We've got 4 powerful tools, and now you know that each one has its own special purpose. It's all about choosing the right measure for the job. So here's your cheat sheet, the big takeaway. Grab the range when you just need a quick and dirty first look. Reach for the IQR whenever you've got skewed data or you're worried about outliers. You'll use variance when you're deep in the weeds of advanced statistical modeling. And for almost everything else, for clear, practical reporting on data that's more or less normally distributed, standard deviation is going to be your best friend.
And please, remember this. These things we've talked about, they are so much more than just formulas to memorize. They are lenses. Each one gives you a totally different view, a unique perspective on the true shape and personality of your data. They let you see the texture, the consistency, and all the interesting little surprises hiding just below the surface.
So the next time you're looking at a set of data, don't you dare stop at the average. Use your new toolkit. Measure the spread. What patterns will you find? What strange outliers will jump out at you? What hidden stories is your data just waiting to tell you?